Every commercial aircraft gets struck by lightning at least once a year. Some get hit multiple times in a single flight. If you've ever been on a plane during a thunderstorm, there's a reasonable chance lightning passed through the aircraft while you were sitting there. You probably didn't even notice. That sounds terrifying. A bolt of lightning carries hundreds of millions of volts. It can heat the air around it to 30,000 degrees Celsius, 5 times hotter than the surface of the sun. It can split trees in half, explode concrete, and kill a human instantly. So why doesn't it destroy an airplane? Why don't planes fall out of the sky every time they fly through a storm? The answer lies in a principle discovered over 200 years ago and engineered into every aircraft flying today. To understand why lightning doesn't harm aircraft, you first need to understand what lightning actually is. Thunderstorms create massive electrical charge separation. Ice particles colliding inside clouds transfer electrons, building up negative charge in the lower part of the cloud and positive charge in the upper part. The ground below, or other clouds nearby, develop opposite charges. When the voltage difference becomes large enough, the air itself breaks down. Air is normally an insulator, but at extreme voltages it ionizes and becomes conductive. A plasma channel forms, connecting the charge centers, and current flows. That's lightning. A typical lightning bolt carries about 30,000 amperes of current. The discharge lasts only milliseconds, but the energy released is enormous, about 5 billion joules per strike. Now consider an airplane flying through a storm. The aircraft is a large conductive object moving through a region of extreme electrical potential difference. It doesn't just passively receive lightning strikes, it often triggers them. As the plane flies through areas of charge buildup, it can initiate a lightning channel. The aircraft becomes part of the discharge path. Current enters the plane at one point and exits at another, typically entering the nose or wingtip and exiting the tail or opposite wing. The plane doesn't absorb the lightning, it conducts it. And this is the key to understanding aircraft lightning protection. In 1836, Michael Faraday demonstrated something remarkable. He built a room lined with conductive metal foil and sat inside while massive electrical discharges were applied to the exterior. He felt nothing. No shock, no current, no harm. This is the Faraday cage principle. When a conductive enclosure is struck by electrical discharge, the current flows through the outer surface of the conductor, not through the interior. The electromagnetic fields cancel out inside. The contents are protected. An aircraft fuselage is essentially a flying Faraday cage. The aluminum skin of a conventional aircraft is highly conductive. When lightning strikes, the current spreads across the outer surface and continues its path to exit the aircraft. It doesn't penetrate into the cabin. Passengers inside experience the same protection Faraday demonstrated nearly 200 years ago. But aluminum skin alone isn't the complete solution. Aircraft designers must ensure the lightning has a clear path across the exterior without encountering gaps or resistances that could cause problems. Every joint, seam, rivet, and connection on the aircraft exterior must maintain electrical conductivity. If current encounters a gap, it can arc across that gap, creating heat and potential damage. So aircraft are designed with bonding straps and conductive connections that ensure continuous electrical paths. The points where lightning typically enters and exits receive special attention. Wingtips, the nose cone, the tail, and engine nacelles are common strike attachment points. These areas often have static discharge wicks, small conductive rods that help dissipate electrical charge gradually and provide preferential attachment points for lightning. The nose cone, or radome, presents a particular challenge. It's made of composite materials that are transparent to radar, which means they're not conductive like aluminum. The radome has embedded conductive strips that route lightning current around it, protecting the weather radar inside. Modern aircraft increasingly use carbon fiber composite materials instead of aluminum. Carbon fiber is strong and lightweight, but it's far less conductive than aluminum. This requires additional engineering. Composite structures incorporate embedded metal mesh or foil layers specifically for lightning protection. These conductive layers ensure the Faraday cage effect is maintained even with non-metallic structural materials. The Boeing 787 and Airbus A350 both primarily composite aircraft, have extensive lightning protection systems integrated into their skins. What about the fuel? Aircraft carry thousands of kilograms of jet fuel in wing tanks. Lightning striking near fuel tanks sounds catastrophic, and historically, it has been. In 1963, lightning struck a Boeing 707 operating as Pan Am Flight 214. The strike ignited fuel vapors in a wing tank, causing an explosion that destroyed the aircraft and killed all 81 people aboard. This tragedy prompted major changes in fuel system lightning protection. Modern aircraft have multiple safeguards. Fuel tank skins are thick enough and conductive enough to prevent lightning from penetrating. Fuel vent openings are designed to prevent flame propagation. Fuel quantity sensors and wiring inside tanks are designed to prevent any spark generation. Many modern aircraft use nitrogen inerting systems that replace oxygen in fuel tank vapor spaces with nitrogen, making ignition impossible regardless of any electrical discharge. These protections have been remarkably effective. Since the implementation of modern lightning protection standards, no commercial aircraft has been lost to a lightning-induced fuel tank explosion. The electrical and avionics systems present another challenge. Lightning creates massive electromagnetic pulses that can induce currents in any conductor, including wiring inside the aircraft. Sensitive electronics could be damaged or disrupted by these induced currents. Aircraft wiring is shielded and routed to minimize lightning exposure. Critical systems have surge protection. Avionics are designed to withstand specified levels of electromagnetic interference. Flight computers have redundant backups. The certification standards are rigorous. Before an aircraft can enter commercial service, manufacturers must demonstrate that it can withstand lightning strikes without compromising flight safety. This involves both analysis and physical testing. Aircraft are subjected to simulated lightning strikes during certification testing. High-voltage laboratories generate artificial lightning and apply it to aircraft structures, while monitoring systems for any failure or malfunction. Every critical component must continue functioning. So what actually happens during a lightning strike from the passenger perspective? Usually, very little that's noticeable. You might see a bright flash through the windows. You might hear a loud bang or feel a slight jolt. The cabin lights might flicker momentarily, but the flight continues normally. The pilots will note the strike in their log. After landing, maintenance crews will inspect the aircraft for any damage. Common findings include small burn marks at strike entry and exit points, sometimes requiring minor repairs or parts replacement. In most cases, the damage is superficial. Paint scorching, small pits in the aluminum skin, minor damage to static wicks. The aircraft is typically back in service after a quick inspection and any necessary repairs. There have been incidents where lightning strikes caused more significant problems. Electrical system anomalies, temporary instrument failures, minor structural damage. But modern commercial aviation has an excellent safety record regarding lightning. Pilots are trained to avoid thunderstorms when possible. Weather radar allows them to see precipitation cells and navigate around the most intense storm areas. Air traffic control helps route aircraft away from dangerous weather, but complete avoidance isn't always possible. When aircraft must fly through areas of lightning activity, they do so with confidence that the engineering will protect everyone aboard. The statistics reflect this confidence. Commercial aircraft experience millions of flights per year. Lightning strikes occur regularly, perhaps 1,000 or more times per year across the global fleet. Yet lightning-related accidents in modern commercial aviation are essentially non-existent. The protection systems work. There's something elegant about the physics here. Lightning is one of nature's most violent phenomena. Temperatures higher than the sun's surface, enough energy to power a city block. A force that terrifies humans on an instinctual level. And yet a simple principle, discovered by a scientist in the 1830s, provides complete protection. The Faraday cage effect requires only that the enclosure be conductive and continuous. Current flows outside. The interior remains safe. Every time you fly through a storm, you're protected by the same physics Faraday demonstrated with his foil-lined room. The aircraft skin conducts, the lightning passes through, You sit inside, completely unaffected. The next time you see lightning from an airplane window, remember that you might be watching a strike hit your own aircraft. And that's perfectly fine. The engineering has you protected. Speaking of electrical systems on aircraft, there's a fascinating backup system that activates when all normal power fails. The ram air turbine drops from the fuselage and generates emergency power from airflow alone. I've covered how that works in another video.